In the last video, we tried to categorize different types of machine learning algorithms, which we show that it can be really difficult and complex. So what is the real question we are asking here?
Well, the real question we want to ask is what drives the future of AI, which is AGI or artificial general intelligence. And the two aspects we should consider in doing that is the quality of data and generalizability. A more important thing to discuss about machine learning models is the quality of data and the generalizability, right?
Exactly. That's what exactly it's boiling down to. The quality of data. How can we measure that? How can we assess that? We already give some hints, like what is the degree of imbalance in the data we have, what is the size of data we have, and all that. And generalizability.
Yeah, and generalizability is so AGI, right? Artificial general intelligence is a dream. And so far, what we have learned about generalizability and transferability. So transfer learning is another domain of machine learning. So what we mean by generalizability is that how well can your model do beyond your training data? Like how good can your model perform on unseen data?
Never seen before, exactly.
For example, like if you're designing self-driving cars and you train the car in the roads in the States, can you drive that car in China, the roads on China?
Exactly. Or
if you have an LLM model, right, which you trained on, say, financial data, but can it write a poem?
Yeah. Can it learn from financial data to say a
About
beautiful
Bukowski,
a very, very meaningful poem?
Yeah, I don't know.
Yeah.
It might happen. Now let's dive into the notion of generalizability without going into much of the mathematics behind it.
Exactly.
And we also try to understand the generalizability notion with respect to the training data, and especially the quality of the training data that we were discussing earlier, right? Well, of course, like the holy grail of machine learning is that you have limited amount of data, maybe not that good quality, but still you can design a machine learning architecture in such a way with great engineering skills that is like highly generalizable.
And this has been started long ago. It started on the domain of statistics, very, very old field. But the focus in statistics was how can we do a lot with limited number of samples.
Yeah.
And as you can see in this diagram,
so understanding the population from a small sample. Estimation theory, right?
Yes, exactly. How can we estimate the population characteristics taking a small samples?
Yeah, I really liked it. Like mapping it back to the classical estimation theory.
Exactly,
right?
Exactly. And then as you can see in this diagram here, the amount of data was very poor back in the day because of not having access to computers, engineering, and etc. But a lot of genius, smart statisticians were able to even generalize into population on that amount of data and derive meaningful information. But the question is, what if you give out of distribution data, never seen before? How would the predictions do?
Yeah, never before seen data, right? Like which you, for example, one of my recent papers, like where we're trying to predict protein ligand binding. And if you have a new kind of a disease associated with a new kind of a protein which weren't like studied before, or there weren't many drugs developed for that protein before, and if you want to design a new drug, then that is kind of not in the training data. You don't have much training data on that, right?
Exactly.
So how can your machine learning perform well in this kind of scenarios?
So the problem is even more complicated than we think. So we initially thought that having more data would help generalizability.
Not necessarily, right?
Exactly.
Overfitting.
Exactly. As you can see here in this diagram, the amount of data is increased twice more than before. And generalizability is just increased a little bit more.
Yeah.
Many reasons. And one of the reasons is the amount of data doesn't matter, as we discussed before. The quality also matters, and the architecture, which Ayan is an expert on.
Yeah, and recently a lot of research. So if you read the recent papers from the top machine learning conferences, there's a lot of papers, like there are a lot of papers dealing with this out of distribution prediction. So this is a really important problem, and we need to solve this thing to take us step forward towards AGI, towards artificial general
Exactly.
intelligence.
So what is our goal? As you said, AGI is like the holy grail that everyone wants to achieve. That's the next wave. But what is the goal? The goal really is, as you can see in this diagram, to be able to generalize further using limited data. And why using limited data? Because we are always going to have limited data. Observation, always, no matter how much you have better microscope.
And data is expensive, man.
Yes, it's expensive.
And also,
all
like,
that.
if you're collecting more data,
Yeah.
doesn't necessarily mean that you're increasing the diversity in that data. So you're getting new kind of data.
Right? Even sometimes by observing a system, you're actually changing its behavior.
Yeah.
So there are little different curses that you need to deal with.
Yeah, and think about humans, right? Moving towards AGI, humans can solve new tasks without being exposed to it like previously. So that
Creativity.
kind of an intelligence, yeah.
Exactly.
Yep.
So here, we're trying to find a balance, and we are trying to ask questions like, what data properties and how much data is needed to have a generalizable algorithm?
Yeah.
And what are the upper bounds? Like, how, given a data set, can we tell what is the maximum amount of generalizability you can have? These are the kind of questions that it needs to be solved before we even talk about AGI.
Yeah, people are trying to like answer this kind of questions, like, and integrating like things like information theory and all that into machine learning to have this kind of answers, right?
Exactly.
Yeah. Okay, since now we have established how we should evaluate machine learning models, not in terms of the approach, but rather in terms of the generalizability and the quality of data it is trained on. Let's look at some of the state-of-the-art models which have gained a lot of popularity recently, how they do in terms of the quality of the data and generalizability.
Exactly. Where do they fall in the diagram?
So deep purpose is a machine learning model which is used to predict binding between proteins and small molecules ligands. But what we saw in our research was that the generalizability of this model wasn't that good.
Exactly. In fact, what was observed was, if you go ahead and give deep purpose, only the patterns of bindings between proteins and ligands, the small molecules, that's enough. Its performance is going to be exactly the same as if you also give it the protein sequences.
Yeah. So it was learning from the drug-target interaction network rather than the molecular structures.
Yes, some sort of a shortcut to learn from.
Yeah, we call it topological shortcuts.
Exactly. So that means that it does well on proteins that have a lot of interactions with drugs, the proteins that we have a lot of known, basically they are targets to many drugs. It does well for them. And then the proteins that do not have many target drugs, the algorithm doesn't predict well enough.
Yeah, yeah. So as a solution, we developed AI-Bind, which learns the binding patterns, the binding mechanism from the molecular structures, and doesn't rely on the topological shortcuts that Babak mentioned. That's the network structure of the drug-target interactions, right? And due to that reason, since you eliminate the topological shortcuts from training, you can predict really well on unseen drugs and unseen proteins in this case.
It's really important to hear that we mention the databases used is exactly the same.
BindingDB data, pretty common.
Exactly the same databases has been used. But ION was able to increase the data quality by finding a smart ways like network-derived negatives.
And unsupervised pre-training, the pre-training we're talking about.
That basically decreases the amount of imbalance in data, forcing the machine learning to not learn shortcuts.
Yeah, yeah.
And that's why we placed AI-Bind a little bit higher in terms of data quality. So that what really changes is not the number of proteins, it's not the number of drugs. It's really some smart ways to increase the quality of
Yeah,
data.
and it's pretty surprising that deep purpose is like humans, right? So if humans can achieve something by shortcuts, they're gonna try to take the shortcuts, and
Exactly.
and the machine learning also tried the same, right?
Yes, it's cheaper. If you learn
Yeah.
shortcuts, you don't need to spend a lot of energy.
Yeah.
Yes. So looking at the food processing paper that we have done, predicting the degree of processing from food, it's pretty generalizable. The generalizability is high because we trained this algorithm only using the USDA model foods, and then we went ahead and tested on thousands of foods from grocery stores on just the food labels.
So beyond your training data set.
Yes, exactly. And it did well.
Mhm.
So then it's generalizable. And the important part here is we are just using a random forest. You don't
Yeah.
really need to use a neural network.
Yeah, yeah. So the feature engineering you did, combined with a random forest classifier and the data pre-processing and the data engineering that you did on the USDA data,
Log
like all,
transformers and all that, yeah.
all that combined like improved the generalizability, and you can use that on like any kind of food items, probably, right?
Exactly. So really depends on the problem. Do not
Yeah.
always search for neural network architectures.
Yeah, if you don't need AI, don't incorporate it. Yeah, yeah.
Yeah.
If a simple regression does your work, go with a simple regression, man.
Yes.
Continuing the discussion that we just had, all the state-of-the-art AI machine learning models can be placed in this data quality versus generalizability diagram. You can see like ChatGPT has a really high quality training data, but the generalizability is okay, pretty good.
Yeah, the ChatGPT, I can see a lot of times it's hallucinating. Like
everyone's talking about it.
Yes,
Hallucination of ChatGPT. I had some examples too.
Yes, a lot of times I'm asking for references for responses, and it just creates references that do not exist, or even very simple tasks like add two numbers, 2 plus 5. A lot of times it cannot do it.
And sometimes the ChatGPT creates URLs that don't work. I don't know where that comes from.
Yeah, and all this comes back to the fact that there are many ways that things do not work, only a few ways that things do work. And when you interact with large language models, because it's your language and you talk with it, you can spot. You can sometimes or often spot that the response doesn't make sense.
Yeah.
Yeah.
And another GPT model, DALL-E, which is used for creating images, creating pictures, right? So I asked DALL-E to create a Led Zeppelin album, and it created this, like where it couldn't even correctly pronounce Led Zeppelin or like have a meaningful album art. So, it completely depends on what kind of training data and what kind of labels you have during this kind of trainings, like whether your model will be generalizable or not. So
Yeah.
generalizability and AGI is something we need to more talk about,
As you can see here, like, Ayan is a Led Zeppelin fan. I'm not, but I like your work. You can see that the AI can't even write Led Zeppelin right.
Yeah.
It even have typo. It even has typo there, and Ayan, you can tell better. Is it by any measure of a stretch of imagination related to Led Zeppelin? What you see here?
No, and the art quality is like bad, man.
So what we are really saying here is, when it comes to art, you can tell it's generalizable or not based on the domain knowledge that you have. And then looking at self-driving cars, they are still struggling to have self-driving cars operating in extreme weather conditions like snow.
Yeah.
And that's why we see a lot of self-driving car companies are in California, where the weather is stable. It's perfect for them to train. So then the generalizability is an issue there as well.
Yeah, just imagine taking those cars on an Indian busy road, like where there are a lot of humans and animals walking around. I
Oh,
don't
yes,
think that's
yes.
good. That is the toughest test.
Exactly. What if the road is shared not only by humans
Yeah.
and all other beings? We will get back to these topics in the future videos as well. The goal today was to set the baseline of how should we look at AI ML algorithms.
Yeah. And in
And
order to achieve our dream of AGI,
exactly,
what
like
we should focus
exactly.
on.
What are the questions to focus on? Like, can we come up with an upper bound for generalizability? Can we quantify data quality, and etc. Uh, and in the next videos, we are going to talk about metrics, performance metrics in machine learning algorithms.
Yeah, sometimes they are deceiving.
Exactly. That's why
Yeah.
we started to first talk about generalizability before talking about performance metrics.
And never judge a book by its cover, and never judge a machine learning model by the accuracy.
Oh, yes, yes, exactly. We will get into that. Until next time, thanks a lot for watching.
And keep up the network thinking.
Indeed.